Welcome to the first annual Symposium on Mitochondrial Health, Health Span, and Aging. The New Energy Crisis by Rob Lustig.
I'm going to kick things off with a relatively short talk about why we're here, okay? As I think you're all aware, genetics hasn't solved our chronic disease problem. And RFK picked up on that and actually turned it into a movement. We are not here as part of that movement. I want to make that very clear. But we are here to talk about how mitochondria matter, how mitochondria are implicated in these various chronic diseases, and what we can do about them in order to hopefully help patients and help society. The talk is obviously the new energy crisis. Everybody knows the old energy crisis. I lived through the 1973 Arab oil embargo. Some of you did too. Okay, but this is our new energy crisis, and it's coming from within instead. It is not functioning. It's not. Whoops. Maybe it is functioning. Okay, there we go. There we go. So I do have these disclosures. I did write these books for the general public. I am chief medical officer to these companies, paid advisor to these others, and an unpaid advisor to Blue Oak Nutraceuticals. Sandeep, you got to do something about that. Okay. So, is mitochondrial dysfunction a common root of non-communicable disease? That's the question that we're trying to answer today, and through what mechanisms and how can we ultimately impact that for the benefit of our patients. Now, I will tell you, mitochondria has gotten a good and also a bad rap. Okay, so here's an article, mitochondrial dysfunction is a bit of a fad. Okay, well, is it? Okay, depends on who you ask. Well, if you ask this guy, okay, he doesn't have a medical degree, but he says he can diagnose mitochondrial dysfunction just by looking at children. I am a mitochondriologist. So the question is, can I do that? And the answer is actually,
and I know what
believe it or not, I can. Okay, because there is a disorder called Kearns-Sayre syndrome. You're looking at a child who has it, and you're looking over 6 years' time, and what you see is ptosis. You see the eyelid now drooping, and also this kid can now not accommodate and see close because of what's known as internuclear ophthalmoplegia. And I have diagnosed 3 kids with Kearns-Sayre syndrome who came in with what looked like type 1 diabetes, but in fact had mitochondrial diabetes just because of their ptosis. So in fact, you can do that, but I don't think that's how RFK is doing it. So we're going to talk a little more about RFK at the end as well, you'll see. So to explain how mitochondria work or don't work, I want to present to you first how this might be important in obesity. So if you'll notice, the trends for obesity continue to go up in adults like crazy, but take a look over here on the right for children. And what you'll notice is that for the 5 to 19-year-old age group, it continues to increase, but notice that the 2 to 4-year-old age group has actually leveled out. Now, why would that be? Very simple. We got juice out of daycare. This is when we got juice out of daycare. So what this says is that this is an environmental construct that, in fact, you can do something if you basically don't overwhelm your mitochondria. Now, here's data that actually supports that this is, in fact, the problem. On the left, we see a graph of human body temperature over the last 150 years, since the Civil War till today. And what you can see is that it doesn't matter if you're black or white, male or female, 40, 50, 60, 70, 80 years old, our basal body temperature has been declining by 1.6 degrees Fahrenheit from 98.6 now to 97.0 degrees. So you all learned that a normal body temperature was 98.6. Well, that is normal, but none of us have a normal body temperature anymore. Now, if you recognize that The reason that you have a body temperature is the heat given off by the inefficient utilization of food energy by mitochondria. About 35% of your food basically gets turned into heat. If you're generating less heat, that means your mitochondria aren't doing their job. And so here's, proof positive data that we've got mitochondrial dysfunction going on across, across the generations. On the right, we have a graph of the fact that laboratory animals in captivity eating the same chow for 25 years have all been increasing in weight. Now, it's not like that we closed down their Disneyland parks, or that somehow they're not being taken for walks. The fact of the matter is that something in the environment that they're exposed to, that presumably we're exposed to also, is actually driving weight gain. And the question, of course, is, what is that and at what level? That's where we are. So that's the first problem. Here's the second problem. We have an epidemic of obese 6-month-olds, and they don't diet and exercise. We even have an epidemic of obese newborns. Okay? 4 separate studies, South Africa, Israel, Russia, United States. There's been a 200-gram increase in body weight over the past 25 years. And when you do DEXA scanning on those babies, turns out it's all fat. So these babies are actually born fat right out of the box. And the question is, how'd that happen? So any hypothesis you want to use to explain the obesity epidemic has to be able to explain this as well, and you can't unless you invoke the mitochondria. Now, the question is, what's happening to them? Well, we now know that there are all of these chemicals in our environment, which we commonly refer to now as endocrine disruptors. You've all heard of EDCs. Some of them are toxic and affect the DNA. We call them mutagens. Okay? And some of them actually increase adiposity, and we call those obesogens. Okay? And here's a sampling of the obesogens in our environment today. Maternal smoking, air pollution, DDT, PFAS, all the way down the line. Of course, my favorite hobby horse, as I told you, used to be fructose. We're going to talk about that in just a second. Okay? But they're all obesogens. They're all driving adiposity exclusive of their caloric content. Okay? Now, how does fructose do it? It inhibits mitochondria at 3 separate steps. It inhibits an enzyme called AMP kinase, which is the fuel gauge on the liver or the brain cell. Okay? And that means that you're not able to induce new mitochondria. Mitochondrial biogenesis is inhibited. It also inhibits this enzyme over here called ACAD-L, acyl-CoA dehydrogenase long chain, which is necessary to take fatty acids and cleave them into the 2 carbon fragments in order to be able to use them for beta oxidation. And also, it inhibits this enzyme here called CPT1A, carnitine palmital transferase 1A, which is the enzyme that regenerates carnitine, which is the shuttle mechanism by which the fatty acids get into the mitochondria for burning in the first place. So the bottom line is that in contrast to glucose, which increases mitochondrial beta oxidation, fructose actually inhibits mitochondrial beta oxidation. Ron Kahn, who runs the Joslin Diabetes Center, famously said about this study of his, the most important takeaway of this study is that high fructose in the diet is bad. It's not bad because it's more calories, but because it has effects on liver metabolism to make it worse at burning fat, read mitochondria. As a result, adding fructose to the diet makes the liver store more fat, and this is bad for the liver and bad for whole body metabolism. The point is that when energy is coming into a cell and the mitochondria can't process that substrate, what happens to it? It has to be diverted. What does it get diverted to? Well, in the liver, it's going to get diverted to fat. The question is, what happens if that's going on in the brain? So we're going to go there in a minute. These obesogens, in the list I just gave you, can alter many metabolic endpoints, some of which we basically attribute to standard obesity, like, for instance, increased food intake, decreased exercise tolerance, basic couch potato. Basically, the behaviors that we associate with obesity are actually results of the defective mitochondrial function rather than the cause. And that's the important thing, is that the biochemistry drives the behavior. Okay? And if you take a look at all these different obesogens and where they work, okay, the bottom line is they all increase this thing here. So this thing is called reactive oxygen species, ROSs. These are throw-offs of mitochondria when they are working poorly. And you will see that ROSs can be toxic to cells, but they can also be signaling to cells. And that's the important point I'm trying to make here, is the signaling aspect. So for obesogens, they're endocrine disruptors. They disrupt signaling pathways that are important in nutrient handling and adiposity. They can be natural, like metals or viruses. They can be anthropogenic, like prescription drugs. They can be environmental, like insecticides, plastics, household chemicals, particulate matter, or they can be food components. Now, you tell me who in America is devoid of exposure to any of these four things. All of us are, susceptible to all of these all the time. Every one of these is a generator of reactive oxygen species. Not one is not. Okay? All of them are. And all of these, therefore, are potential mitochondrial toxins all by themselves. So let's spend a moment on reactive oxygen species. Now, mitochondria make reactive oxygen species. They can't help but make them. In fact, I'll show you on the next slide, 11 different enzymes throw off ROSs. Okay? It's part of the deal. Okay? The only way to have no ROSs is to be dead. Okay? You want to be alive, you're going to make ROSs. The question is, what do you do with them? Okay? And what you can see here is that different things that cause obesity and different things that are associated with dementia, for that matter, all ultimately impact this ROS pool. And there are ways, of course, getting rid of the ROSs having to do with antioxidants. So here are those 11 separate mitochondrial enzymes that all, wherever you see red, that's ROSs. Basically, complex 1, complex 3, doesn't matter, you're going to have to deal with them. And the question is, how do you deal with them? So ROSs are both a toxic molecule when they build up to too high a level, because they can cause lipid peroxidation, protein denaturation, and ultimately cell death. Or they can be signaling molecules. So ROS can signal PI3 AKT for metabolism. They can signal NF-kappa B for inflammation. They can signal NFR2 for growth and cancer. They can signal calcium for neurotransmission. And ultimately, ROSs inhibit mitochondrial ATP production because they are an autocrine, that is a generated in the cell signal for the mitochondria to divert away from carbon dioxide and ATP and toward storage of some sort, whether it be fat in the liver or glycogen in the brain. Okay? So food consumption can up your ROSs, obesogens can up your ROSs, and ultimately they can impact on things that we can measure, like increased insulin, food intake, gluconeogenesis, all leading to nutrient storage. Okay, so why does this matter? Well, I'm going to present to you now a hypothesis. This is not written down anywhere yet, okay? But I'm going to vet it for you, and I would love your input on it, because I've talked with several neurologists and psychiatrists about this, and they go, yeah, this makes a lot of sense. So I would very much like it, especially Aaron, you're on deck here. Okay. So first of all, advanced glycation end products are ROS generators, and they are associated with cognitive decline. They do all these things inside neurons. It's also true for Parkinson's and possibly even for Huntington's. So here's how it works. Here's a mitochondria. And as you know, mitochondria take glucose. We're not going to put the glucose on because otherwise it gets too messy. Okay, but you know that glucose is going in, and ATP is coming out along with carbon dioxide. That's what mitochondria do. They turn glucose into ATP and carbon dioxide. They burn it all the way to completion. Okay? In the process, they make these ROSs through those 11 enzymes I just talked about. Now remember, ROSs are a signal to the cell to divert. So the more ROSs that build up, the more you're going to move glucose away from mitochondria and toward diversion. Well, take a look at this list over here. Every one of these is an ROS generator. Every one of these is associated with Alzheimer's disease. So the question is, are we just awash in this huge ROS pool coming from the outside and coming from the inside that basically tell the mitochondria, store instead of burn? Now, the only way to deal with it is to get rid of the ROS pool. And the only way you can do that is with the antioxidants. The problem is, this hypothesis has been around since 1956. But the problem is that all the studies trying to give antioxidants to either Alzheimer's animals or Alzheimer's people have not worked. Because if they had worked, you'd have heard about it. And they haven't worked. And the question is, did they get to where they were going, and were they able to actually get rid of the ROSs in the first place? Chances are no. So what this means is that because these mitochondria are now in sort of idle mode rather than in burning mode, okay, what that's doing is it's reducing oxidative phosphorylation, reducing electron transport chain passage, and that ultimately reduces ATP synthase. So you end up with reduction in ATP production. So now your cell is at risk. Your cell is vulnerable because it's not keeping up with the ATP needed to run all of the machinery, all the motor things that go on inside a cell, whether it be tubules or whether it be neurotransmission, et cetera. So what that might mean? Well, maybe some brain fog, maybe some inattention, maybe some lack of cognition. Now, that's step one. Now step two. Throw on top of that stress, sleep deprivation, or glucocorticoids, all of which basically raise your cortisol or cortisol mimics. And it turns out what cortisol does is it makes the neuron have to work harder. It increases ATP utilization, causes a neuronal hypermetabolism, as demonstrated by our colleague Dr. Martin Picard at Columbia University. So now you've got reduced ATP production and increased ATP utilization. Now the cell's really at risk. And now you end up with neuronal dysfunction, whether it be cognitive impairment or full-blown depression. Well, it turns out that this guy, amyloid precursor peptide, which is in all of our cells in our brain and in other organs as well, like pancreas, okay, it is cleaved based on the oxygen availability, the ATP availability within the cell. And when the ATP goes down, you end up with more amyloid. And amyloid, of course, is what ultimately leads to the plaques. In addition, the phosphatau 17 has now been shown to sort of be the cage for the glycogen that got formed that shouldn't have, because you should have burned the glucose all the way to completion. And so what you end up with is plaque formation and circuit failure. On top of that, the ROSs generated from this thing here are going to stimulate NF-kappa B and the inflammasome, leading to inflammation. And now you've got plaque formation and inflammation leading to neuronal death. And the question is, does that hold up and does that pass muster? The answer is every one of those arrows has data behind them. The question is, do they all fit together in a narrative or in a proof? And that's what I am vetting with the rest of you today. Okay. So I'm going to leave you with this idea. Now, let's turn back to RFK. It's been a busy week, hasn't it? Tylenol, what do you think? Cause of autism? There's a nugget of truth in everything he says. Okay? The problem is only a nugget, okay? Not the mother lode. And so the question is there truth to this concept? Well, if you actually look at the data from acetaminophen in pregnancy, the hazard risk ratio for acetaminophen exposure and autism in pregnancy is, depending on the study, somewhere between 1.05 and 1.2. So it's not 1.0. That would be identity. That would mean no effect. But 1.05 to 1.2. So a 5 to 20% increase in risk, according to the 46 studies that went into these meta-analyses. That's not nothing. On the other hand, for a public health directive, you need to be at a hazard risk ratio of 1.3 or higher, okay, but as the public health community. So basically, that's why you're getting these confusing messages, because there is a signal, it's just not a very big signal. And the question, of course, is, well, if Tylenol is the real story, why is it not a very big signal? And the answer is because Tylenol is not the story. Let me show you why. So here is Tylenol, right here, APAP, acetaminophen, causing reactive oxygen species, leading to cell damage in the fetus from mother's ingestion of Tylenol. That is likely true, and we actually have data to support that. The question is that what's going on? So, in fact, ROSs have been, and oxidative stress, have been associated with autism spectrum disorder by many other investigators. This is not a new idea. The problem is, it's not just Tylenol. It's any ROS generator. And there are a whole bunch of them. And so that's why the data is buried within the morass of all of the other ROS generators. It's not just Tylenol, it's all of these, and that's why the signal is so garbled. Really, the way to look at it is to have a specific experimental model for autism, and there is one. It's called valproate, valproic acid, also known as Depakote. Okay, this is an anti-seizure medicine that we give to babies and infants in order to stop their seizures. And it is a mega generator of ROSs, and it is the proof positive for autism in an animal model. And so there is definitely a high signal for valproate and autism in humans. And it's because of the ROS generation. So it's not Tylenol that's the problem. It's any ROSs, and God knows, look how many we're exposed to, all because of mitochondrial dysfunction and what's going on in the environment. So he's not right, but he's also not wrong, just like everything he says. So with that, my summary, our new energy crisis is mitochondrial. RFK can't tell mitochondrial dysfunction by looking at them, but I can. ROSs are normal products of mitochondrial metabolism, but also feedback on ATP generation, and obesogens add to the cellular ROS pool, which is how they're obesogens. Fructose is an obesogen that alters AMP kinase, which also reduces mitochondrial ATP generation, and we're going to hear about that from our two of our speakers today. Brain ROSs, I believe, reduce mitochondrial ATP production, and then you throw on top of that inflammation from the stress and glucocorticoids, which increase ATP utilization, and now you've got an energy crisis. And the reduced ATP within the cell leads to the plaques, add the inflammation, and that leads to the neuronal loss and dementia. And autism is not due to Tylenol per se, but definitely could be due to mitochondrial dysfunction and ROSs for any cause. So with that, I hope that sets the table for you as to how important mitochondria are, how important ROSs are. You're going to hear a lot about various mitochondrial signals and their distress pathways, and what we can do to try to heal them in the process, hopefully healing ourselves as well. That is what today is about. Yes, question. I can't hear you. Is that a form of what? Fruit? Fructose is the sweet sugar in fruit. But when you eat fruit, you're also getting the fiber, and the fiber diverts the fructose away from being absorbed and actually goes to the microbiome, where the microbiome chews it up. So even though you ate it, you didn't get it. So when it's whole fruit, it's not a problem. When you turn it into fruit juice, it is a problem. And that's why whole fruit is associated with diabetes prevention, whereas fruit juice is associated with diabetes development. Okay? So with that, I thank you.
Stay tuned for the second annual Symposium on Mitochondrial Health, Health Span, and Aging.